Module 3. Lecture B. Dicts and Sets. By the end of this lecture, you will be able to explain how hash tables underpin Python dict and set behavior, analyze the expected time complexity of lookups, insertions, and deletions in dicts and sets, and select appropriate key types and usage patterns to maintain efficient hash-based operations. Hash table foundations. Hashing and buckets. Dictionaries and sets can be thought of as storage made of many numbered slots, each holding a key value pair or a single element. To decide which slot a key, like a username, should use, Python applies a hash function that turns the key into an integer fingerprint. This hash value tells Python exactly which bucket in the storage array to use. As a result, Python can jump directly to the correct location instead of searching through all keys, making data access very fast and efficient. In a hash table, buckets are important because they do not hold the data themselves. They simply point to where the data is stored. Each bucket can contain multiple entries that share the same hash location. When you add a key to a Python dictionary, Python computes its hash, chooses a bucket, and stores the key and its value there, then later repeats the hash and bucket lookup to retrieve it. Sets work in a similar way, but they store only the element, which allows fast membership checks without scanning the whole collection. A hash table works like a library catalog that assigns each book a number based on its title and author, which tells you exactly where to find it on the shelves. In the same way, Python uses a hash value to decide which bucket to use for each key in a dictionary or set. This lets Python quickly locate, add, or remove entries by going straight to the right place instead of searching through everything. The efficiency of these operations depends on the hash function spreading keys evenly across the available buckets. Python code, hashing and buckets. We want to visually demonstrate how hashing maps keys into buckets so learners can see how a hash function decides where each key is stored. The goal is to show that different keys may end up sharing the same bucket or using separate buckets, depending on their hash values. By doing this, we connect the way a dictionary behaves, such as how it looks up and stores values, with the underlying positions of hash buckets that make these operations efficient. If needed, we can install any required library to support this demonstration. We define a hash table with a size of 8, meaning it has 8 available slots for storing data. To implement this, we create a list of 8 empty lists, where each empty list acts as a bucket. Each bucket will hold the keys that map to it based on their hash values. This structure lets us organize and manage data efficiently by grouping keys into these predefined buckets. We use a helper function to decide which bucket a key belongs to in a hash table. This function takes the key and the total number of buckets, then applies Python's built-in hash function to the key. It then takes the remainder of that hash value when divided by the number of buckets. That remainder is used as the bucket index, which spreads keys across the available buckets based on their hash values. We begin with a list of keys, such as the names Alice, Bob, Carol, and Dave that we want to store in a hash table. For each key, a helper function uses Python's built-in hash operation combined with the table size to compute a bucket index. The key is then placed into the bucket at that index in the list of buckets. By repeating this for all keys, we distribute them across the buckets according to their hash values, showing how each key is mapped to a specific location in the hash table. The code first prints a header that explains how the upcoming buckets are organized. This header prepares the reader to understand the layout of the buckets that will be shown next. It clarifies how keys are distributed across the different buckets. As a result, the reader knows exactly what information the following output represents. We loop through each bucket in our list, using a function that gives us both the bucket's position and its contents. For every bucket, we print a message showing its index and the keys it holds. This lets us see how keys are spread across the buckets and makes it easy to notice which keys end up in the same bucket and which ones are stored separately. To look up the key Carol in a hash table, we first compute which bucket it belongs to. A helper function takes the key and the table size, calculates the key's hash value, and then uses the remainder after dividing by the table size as the bucket index. This index tells us exactly which bucket stores the key. By printing out that Carol is found directly in that bucket, we illustrate how hash tables enable efficient key lookups by jumping straight to the correct location. This script illustrates how hashing assigns keys to buckets, which is the core idea behind Python dictionaries. It creates a table with 8 buckets and uses a simple hash function to decide where each key belongs. The keys Alice, Bob, Carol, and Dave are inserted, and the script reports which bucket each one goes into, showing that some keys may share a bucket while others do not. It then demonstrates that looking up a key such as Carol goes straight to the correct bucket, highlighting how hash tables enable efficient data retrieval. Handling collisions. In a hash table, each key is sent to a bucket using a hash function, but different keys can sometimes land in the same bucket, causing collisions. This happens because a large set of possible keys is being squeezed into a limited number of buckets, so some overlap is unavoidable. Instead of trying to eliminate collisions, a good hash table design focuses on handling them efficiently so that lookups and insertions stay fast. In Python, this collision management is especially important for the performance of dictionaries and sets as they grow and more keys share similar hash values. Hash tables handle collisions mainly in 2 ways: chaining and open addressing. In chaining, each bucket can hold several key value pairs, so all items that hash to the same bucket are stored together. In open addressing, which is how Python works, each bucket holds only one entry. When a collision happens, the table follows a specific pattern to search for the next free bucket, and it uses that same pattern when looking up a key to either find it or confirm it is not in the table. Collision handling in hash tables strongly affects performance because many collisions force the system to check multiple locations, slowing operations. Python reduces this problem by using efficient probing strategies and resizing the underlying array to avoid overcrowding. As long as hash values are well distributed and the table manages its capacity, dictionary and set operations remain fast, even when collisions occur. Python code. Handling collisions. In this lesson, we will use a very small custom hash table to demonstrate how hash collisions occur and how probing works by searching the next available slots when two values map to the same position. We will then compare how this simple table behaves with the way a normal Python dictionary handles the same situations. You do not need to install any extra packages because the script relies only on Python's built-in features. We begin by choosing a hash table size of 5 on purpose so that collisions happen often. This small table means many different keys will be assigned to the same positions. As a result, we can clearly observe what happens when collisions occur. This setup lets us focus on how collision resolution methods, such as probing, work in practice. This function uses a simple hash method to find the bucket index for a key. It first computes the key's hash value with Python's built-in hash function, then takes that result modulo the table size so the index stays within the table's bounds. This process spreads keys across the available slots, but with a small table size, collisions are more common, which is intentional here to illustrate how collisions occur. The insert operation for this hash table adds a key and its value using linear probing to resolve collisions. It first computes an index by taking the hash of the key and reducing it to the table size, then tries to place the pair in that slot. If the slot is already taken by a different key, it moves forward one slot at a time, wrapping around to the start if needed, until it finds an empty slot or one with the same key. This process allows insertion even when collisions occur. If the search returns to the original index without finding space, the function reports that the table is full and no more items can be inserted. The loop keeps probing the hash table until it finds either an empty slot or a slot with the same key. At each step, it checks whether the current position is occupied by a different key, and if so, it moves to the next position. The index is updated by adding 1 and wrapping around to the start when it reaches the end of the table. If the search returns to the original starting index, it concludes that the table is full and raises an error because no more items can be inserted. After probing to find the correct index, the code stores the key and its value in that position in the hash table. This means that even if the first index was already taken because of a collision, the key value pair is moved to the next free slot. By doing this, the hash table keeps all entries properly placed and maintains the integrity of the data structure. The lookup function in a hash table finds the value for a given key by first computing an index with a hash function and using that as the starting point. It remembers this starting index so it can detect when it has searched all the way around the table and returned to the beginning. This mechanism lets the function handle collisions where different keys map to the same index by probing forward through the table until it either finds the key or confirms that the key is not present. The code searches a hash table by probing through its slots to find a given key or an empty position. For each slot, it first checks whether it is occupied, and if so, compares the stored key with the one being searched. If the keys match, it returns the associated value, meaning the key was found. If they do not match, it moves to the next slot, wrapping around the table as needed. This process continues until it either finds the key or returns to the starting position, which indicates the key is not present in the table. In this part of the code, if the lookup operation cannot find a key after checking the hash table, it returns a special value of none. This return value clearly indicates that the key is not stored in the table. The calling code can then detect this result and handle the missing key in an appropriate way. We begin by creating an empty hash table, which is a fixed size list where each position starts out as empty. In this example, the table size is set to 5, so there are 5 available slots. Every slot is initialized to a special empty value to show that nothing is stored there yet. This fixed structure is important because when two keys map to the same position, we can handle the collision by probing forward through the table to find the next available slot for the new key value pair. We begin by creating two lists, one holding the keys AA, BB, and CC, and the other holding their corresponding values 10, 20, and 30. These key and value lists define the pairs we will insert into a hash table. The table is intentionally small so that inserting these pairs will cause collisions. This setup lets us clearly demonstrate how the hash table handles those collisions when multiple keys map to the same location. We loop over each pair of keys and values using a function that pairs them together, and for each pair, we compute a bucket index by applying a simple hash function to the key. This index shows where the key is intended to go in the hash table. We then call the insert function to actually store the key and value in our custom hash table. If the initial bucket is already taken, the insert function resolves the collision by probing for the next available slot so that every key value pair is successfully stored. We now show the final layout of our custom hash table after resolving collisions with linear probing. This output displays the table with all key value pairs inserted and placed into their final positions. By examining this printed state, we can see how collisions were handled by moving to the next available slots. This visual check helps confirm that our collision handling strategy is working as intended. We set the search key to the value we want to find in the custom hash table, then call the lookup function with the table and this key. The lookup function uses the same probing strategy as the insert operation to locate the key. If it finds the key, it returns the associated value, which we store in a variable. Finally, we print a message that reports whether the key was found, and if so, what value was returned. We use a dictionary comprehension in Python to build a dictionary by pairing each key from one list with the matching value from another list. The comprehension goes through both lists at the same time and creates key value pairs automatically. After creating this dictionary, we look up the entry for the key CC to retrieve its associated value. This shows how Python's built-in dictionary efficiently finds values based on their keys. Even in situations where a custom hash table might struggle with key collisions. Finally, the value found for CC is printed as the result. This script shows how a custom hash table handles collisions using linear probing. It uses a very small table so that different keys map to the same initial bucket, computed by taking the hash of each key and reducing it to a table index. When a collision occurs during insertion, the script moves forward through the table to find the next open slot, then prints the intended bucket and the final layout to show where each key value pair ends up. It also performs a lookup to illustrate how the same probing pattern is used to find a stored value. Finally, it compares this manual collision handling with Python's built-in dictionary, which stores the same keys and values without requiring the programmer to manage collisions directly. Growth and capacity. A hash table is like a set of slots that can each store data, and its capacity is the number of these slots. As you add more items, the table fills up, and the load factor describes how full it is. A low load factor usually means faster lookups, while a high load factor can slow them down because of collisions. To keep performance good, Python dictionaries and sets automatically resize themselves before they become too crowded. In a hash table, growth means occasionally creating a larger array of slots and redistributing the existing keys into it. In Python, this resizing happens automatically when the load factor reaches certain thresholds, and the new table size is usually a multiple of the old one to keep operations efficient. Although resizing is more expensive than a single lookup or insertion, it happens rarely enough that the cost is spread out over many operations. As a result, programmers can keep adding items without needing to manage resizing or worry about sudden performance problems. In hash-based structures like dictionaries and sets, memory usage can jump when the table resizes to hold more entries, but this also creates extra space and lowers the load factor. That extra capacity allows many more insertions before another resize is needed, which helps keep operations fast. Because they automatically adjust their capacity, these structures work well for dynamic workloads, such as caching web requests or tracking active users, and remain efficient as data volumes change. Python code, growth, and capacity. This section demonstrates how a dictionary grows as you insert new items. Most insert operations are smooth, but occasionally the dictionary capacity increases in a jump, causing a brief, more expensive growth step. These rare growth events allow the average time to access items in the dictionary to remain nearly constant. No extra installation commands are needed because the script relies only on built-in Python features. We begin by importing the system module, which gives us access to system-specific settings and functions. In this script, we use it to check the approximate memory size of a dictionary in bytes. By doing this, we can observe how the dictionary's memory usage changes as we add more entries. We begin by creating an empty dictionary that will act as an address book. In this structure, each key represents a unique address, and each value stores the name of the resident at that address. Starting with an empty dictionary lets us add entries over time as needed. This simple setup allows us to observe how Python dictionaries grow and adjust their capacity as more key value pairs are inserted. We choose to perform 5,000 insert operations, meaning we will add 5,000 entries to our dictionary, like growing an address book. Setting this fixed number lets us control the size of the example. As the dictionary grows, we can then observe how its memory usage changes with the increasing number of stored entries. We choose a set of checkpoints, which are specific moments when we measure the dictionary's size and memory usage. These checkpoints let us track how the dictionary grows as we add more entries. By looking at these points, we can see when the dictionary changes its internal structure, such as resizing to hold more data. This approach helps us understand how efficient dictionary operations are and how their behavior evolves over time. This line prints a header in the console to introduce a table of results. It defines 3 columns: how many entries are in the dictionary, its approximate memory size in bytes, and a brief comment on its growth stage. This header helps the listener interpret the values that will be shown at each checkpoint as the dictionary grows. We run a loop from 1 up to 5,000 to simulate adding entries to an address book stored in a dictionary. In each iteration, we create a fake house entry by using a key that combines the current house number with Main Street and a value that labels the resident with that same number. Each new key-value pair represents a house and its resident. By repeatedly adding these entries, we can observe how the dictionary grows and how it manages memory as more data is inserted. This part of the code builds an address book by adding entries to a dictionary. Each entry uses a house number combined with the street name as the key, written as a string, like 1 Main Street or 2 Main Street. The value for each key is another string that says resident, followed by the same house number. By repeating this for every house number in a given range, the dictionary grows to represent different residents, each uniquely identified by their street address. At certain predefined house numbers, the program checks whether it has reached a checkpoint and, if so, triggers specific actions. At these points, it reports the dictionary's approximate size and adds a brief comment about its current growth stage. This process is used to show how the dictionary's memory usage changes as more entries are added over time. To estimate how much memory a dictionary uses, we can call the getSizeOf function from the system module. This function returns an approximate size in bytes, giving us a sense of the dictionary's current capacity. By checking this size as we add more entries, we can see how the dictionary grows and monitor the efficiency of our dictionary operations as the number of items increases. The code builds a short comment that explains how the dictionary is growing and when it might resize. At small sizes, such as 10 or 50 entries, it notes that the dictionary is just starting to grow and still has light load with spare capacity. Around 100 and 500 entries, it suggests that the table has likely resized and expanded to handle more items and reduce collisions. At 1,000 entries, it points out that there is now a lot of extra space for future inserts. By 2,500 entries, it observes that the load factor is rising again and another growth step may be close, while for any other size, it simply states that the dictionary is at its final size and ready for more growth. The code reports how many entries are currently stored in the dictionary and its approximate memory usage in bytes, then adds a note about the dictionary's growth stage. By observing this output as more entries are inserted, you can see how the dictionary's memory usage changes over time. This reveals how it resizes internally and how its capacity is managed as it grows. This script shows how a Python dictionary's memory usage changes as many entries are added. As you insert thousands of items, such as entries in a simple address book, the dictionary occasionally resizes its internal storage to keep lookups fast. These resizes cause noticeable jumps in memory use at certain points, like around 50, 500, and 1,000 entries. After a resize, the dictionary has extra capacity. Dict operation costs. Lookup time costs. When we talk about the time it takes to look up a value in a Python dictionary, we mean how quickly Python can check if a key exists and return its value. A dictionary is efficient because it uses hashing to map each key to a position in an internal array. This design allows lookups to run in constant expected time, meaning the average number of steps to find a key stays about the same. As a result, dictionaries remain fast and responsive, even when they contain very large numbers of entries. Dictionary lookups in Python are usually considered constant time, but this is an expectation, not an absolute guarantee. Different keys can sometimes hash to the same location, causing collisions. When that happens, Python must probe nearby slots to find the correct key or confirm it is missing, which takes extra work. In a well-managed dictionary, collisions are rare and lookups stay fast. But if many keys cluster together or resizing is delayed, lookup time can increase, leading to the rare worst-case scenarios people sometimes discuss. In programs that rely on dictionary lookups, you can usually treat these operations as constant time, as long as certain conditions are met. This makes dictionaries suitable for tasks like authentication or URL routing that need fast access under heavy load. To keep performance high, avoid designing keys that cause many collisions, and let Python handle resizing the dictionary as it grows. Knowing that lookup speed depends on the balance between the number of stored items and the dictionary's capacity helps you judge scalability and decide when dictionaries are appropriate for frequent access. Python code. Lookup time costs. We want to show that dictionary lookup time stays about the same even as the dictionary grows. To do this, we compare how long it takes to look up items in a small dictionary versus a large one using timing measurements. By examining these results, we can see that the average time to find an item increases very little, even when many items are stored. This demonstrates that dictionary lookups are efficient and scale well with size. This script runs using only Python's built-in modules, so you do not need to install anything extra. All the features it relies on are already included in the standard Python library. As a result, you can execute the code right away without using any installation commands. We begin by importing the time module so we can measure how long operations take. This module lets us record the start and end times of actions in our program. By using it, we can accurately determine the duration of dictionary lookups. This timing information helps us analyze and understand the efficiency of dictionary access in Python. We create a small dictionary with 1,000 entries, where each key is a user label made from the word user, an underscore, and a number from 0 to 999. Each key maps directly to its corresponding number as the value. This structure represents a simple mapping from user identifiers to numerical data. It also provides a practical example we can use later to compare how quickly lookups work when the dictionary size changes. We build a large Python dictionary with 1 million entries, where each key is a string like user, underscore, followed by a number, and each value is that same number. The keys range from 0 up to just under 1 million. This structure is used to test how efficiently Python can perform lookups when the dictionary is very large. By measuring performance in this setup, we gain insight into how dictionary operations scale as the number of entries grows. function starts by defining a helper that measures the average time needed to look up keys in a dictionary. It first chooses an existing key by taking the first key from the dictionary, representing a typical successful lookup. It then defines a missing key using a string that is not in the dictionary, representing an unsuccessful lookup. These two keys are used to compare how long it takes to find a key that is present versus one that is absent. To measure how long a dictionary lookup takes, we first record the current time using a high-precision performance counter. We then run a loop a chosen number of times, and in each iteration, we access the dictionary with a key that we know is present. After the loop finishes, we record the time again. Subtracting the start time from the end time gives the total duration of all the lookups, which tells us the time cost of repeatedly accessing an existing key in the dictionary. We measure how long it takes to check for a missing key in a dictionary by recording the start time with a high-precision timer, then running a loop a set number of times. In each loop iteration, we test whether a key that is not in the dictionary is present. After all repetitions are finished, we record the end time with the same timer. The difference between the end and start times gives the total duration of all these membership checks. This total time can then be used to compute the average time for a single lookup attempt. To find the average lookup time in microseconds, take the total time spent looking up existing keys and divide it by the number of repetitions to get the average time per lookup in seconds. Then, multiply this value by 1,000,000 to convert it to microseconds. Repeat the same process for lookups of missing keys. Comparing these two average times in microseconds makes it easier to judge the efficiency of dictionary lookups. This code prints a summary of how long it takes to look up keys in a dictionary, both when the key is present and when it is missing. It uses formatted text to show the dictionary's label and the average lookup time in microseconds for each case. The results demonstrate that dictionary lookup time stays roughly constant, whether or not the key actually exists. We repeat the lookup operation 200,000 times to get reliable timing results without making the program run unnecessarily long. This large number of repetitions lets us average the timing over many trials. As a result, any unusual single measurement has less influence, and we obtain a more stable and accurate estimate of the average lookup time. This code measures how long it takes to look up items in a small dictionary. It calls a timing function with a dictionary of about 1,000 keys, a label describing this dictionary, and the number of repetitions to run. By doing this, it evaluates how quickly the dictionary can retrieve values for keys that exist and check for keys that are missing. Overall, it provides insight into the efficiency of dictionary lookup operations for this dictionary size. We now measure and display lookup times for the large dictionary. A timing function is called with the dictionary that has 1,000,000 keys, along with a label and the number of repetitions. This function computes the average time to find a key that exists and to check for a key that is missing. These results show how efficient dictionary lookups remain, even when the dictionary contains a very large number of entries. This script shows that Python dictionary lookups are very fast and stay almost constant in time, even as the dictionary grows much larger. It compares a small dictionary with about 1,000 entries to a large one with about 1,000,000 entries. For each dictionary, it measures how long it takes on average to find an existing key and to check for a key that is not present, repeating these operations many times. The results show that the average lookup time, measured in microseconds, is similar for both sizes, demonstrating that Python's dictionary implementation keeps lookup time largely independent of the number of stored items. Update. Operation costs. When you update a dictionary, you are usually adding new key value pairs, changing values for existing keys, or removing keys. These operations rely on the same process as lookups, where the dictionary uses the key's hash to find its position in an internal array and checks nearby slots if needed. Because of this design, the average time to add, update, or remove a key stays roughly constant, regardless of the dictionary's size. This efficiency makes dictionaries well-suited for tasks like caching, inventory tracking, or managing student records. As a dictionary grows, it occasionally needs to resize its internal storage by allocating a larger array and rehashing all existing keys, which is an expensive operation. However, this resizing does not happen on every insertion, only once in a while. Because most insertions are simple and fast, the average time per insertion stays roughly constant. This means that even as a dictionary expands to hold more data, its overall performance remains efficient. When a key is deleted from a dictionary, the slot is not simply cleared, because that could break the probing sequence used to find other keys. Instead, the slot is marked as inactive but still considered during probing. Over time, this can increase the number of probes, so the dictionary occasionally performs maintenance, such as resizing, to stay efficient. Even with these details, deletions and updates still run in constant time on average, which keeps operations fast in dynamic systems like managing changing e-commerce orders. Python code, update operation costs. In this activity, you will explore how dictionary update costs behave when you perform many insertions, including the occasional expensive resize. You will see that individual updates still feel fast even as the dictionary grows larger, because most operations are quick and only some trigger resizing. You will compare the time per operation for small and large batches of updates to observe how performance changes with scale. To support this analysis, make sure you have the numerical and plotting libraries installed using the standard Python package manager. We begin by importing the time module from Python's standard library so we can measure how long operations take. This module lets us record the current time at different points in the code. By comparing these time values, we can calculate the duration of specific operations. In this script, that timing information is used to evaluate the efficiency of dictionary updates. We define a helper function to measure how long it takes, on average, to insert items into a dictionary. It records a precise start time, creates an empty dictionary, then repeatedly inserts numbers as both keys and values up to a given count. After all insertions are done, it records the end time and computes the average time per insertion by dividing the total elapsed time by the number of inserts. The function prints a formatted summary with a label, the number of inserts, and the average time in seconds, rounded to 8 decimal places. and then returns this average for further analysis or comparison. We begin by running the insertion time measurement function on a small batch of about 1,000 entries as a warm-up. This initial run is important because it absorbs startup costs that could distort our timing results. By priming the interpreter in this way, we reduce the impact of early overhead. As a result, the insertion times recorded for the later, larger batches are more stable and accurate. We measure how long it takes, on average, to insert 50,000 items into a dictionary. A helper function records the total time for all insertions and then computes the average time per item. This average is stored in a value called the median average, which will later be compared with results from other batch sizes. We now measure how long it takes to insert a large number of items into a dictionary. To do this, we use a helper function that inserts 200,000 items, and we label this test as large batch inserts. By timing this process, we can see how insertion performance changes as the dataset grows. This gives us insight into how efficient dictionary operations remain at larger scales. To compare how efficiently dictionary updates run at different scales, we look at the average insertion times for medium and large batches. We compute a ratio by dividing the large batch's average time by the medium batch's average time. If the medium batch average is 0, we set the ratio to 0 to avoid a division error. We then print this ratio, rounded to 2 decimal places, to clearly show the performance difference between the two batch sizes. We build a dictionary of user scores where each entry has a key made from the word user, an underscore, and a number from 0 up to 99,999, and each key is mapped to its matching number. This large collection is used to show that changing the values of keys that already exist in a dictionary remains very fast. Even when the dictionary holds many entries, updating those existing keys is still efficient. We begin by recording the current time with a high-precision timer to mark the start of our measurement. Then we run a loop 100,000 times, and in each pass, we update the dictionary of user scores by increasing the value for each user key, setting each score to its index +1. This process illustrates how quickly existing entries in a dictionary can be updated in place. After the loop finishes, we record the time again so we can determine how long all of these update operations took in total. To find the average time for each overwrite operation, we subtract the start time from the end time to get the total duration of all updates. We then divide this total time by 100,000, which is the number of operations performed. This calculation gives the average time taken for a single update to a key in the dictionary. Finally, we display this average formatted to 8 decimal places to provide a precise measure of performance. This script measures how fast Python dictionaries handle inserting and updating items as they grow larger. It first warms up by inserting 1,000 items, then times the average insertion cost for tens of thousands and hundreds of thousands of entries. The results show that individual insertions stay very fast, with only a slight increase in average time as the dictionary size grows, which reflects the efficient internal resizing. The script also shows that updating existing keys remains extremely quick even with 100,000 entries, demonstrating that Python dictionaries can manage large datasets while maintaining fast access and update times. Iterating dictionary views. When you iterate over a dictionary, each entry is processed in constant time because the dictionary is built on a hash table. Internally, it uses an array of slots and simply scans through them, visiting only the ones that are filled. As a result, the total time to iterate is linear in the number of elements, so doubling the entries roughly doubles the time. This approach is efficient because it follows a cache-friendly access pattern and does not need to repeatedly hash or search for keys, instead just skipping over empty slots. Dictionary views for keys, values, or items are efficient, dynamic snapshots that reference the original dictionary without copying its data. Creating these views is cheap, but iterating over them still takes time, proportional to the number of elements you go through. As the dictionary grows, iterating over its views takes longer simply because there are more entries to process, not because the views themselves become more complex. The views always stay in sync with the current contents of the dictionary. When you iterate over a dictionary and combine that with other operations like lookups, insertions, or deletions, the performance can quickly become linear or worse. Repeatedly scanning all keys in a large dictionary has a linear cost each time, which can outweigh the benefit of direct access. Adding constant time updates during this scan only increases the total work as the dictionary grows. In practice, it is important to remember that iterating over dictionary views is inherently linear, so you should design algorithms to avoid unnecessary passes over large datasets. Python code. Iterating dictionary views. We want to show how iterating over a dictionary scales as the dictionary grows. By timing iteration over keys, values, and key-value pairs for different dictionary sizes, we can compare their behavior. In simple tests, when we double the number of entries, the time it takes to iterate roughly doubles as well. This demonstrates that iterating over dictionary views behaves in linear time with respect to the number of items. This note explains that you do not need any pip install commands because the script only uses features that come with Python by default. In other words, it relies entirely on the standard library and does not depend on external packages. As a result, the code is simpler, easier to run, and works in any normal Python setup without extra installation steps. We begin by importing the time module so we can measure how long operations take to run. This module offers tools for working with time, and here it is specifically used to record execution time. By timing how long it takes to iterate over different views of a dictionary, we can compare their performance. This helps us understand the efficiency of these operations in a precise quantitative way. We define a helper function called buildInventory that takes a single input called size and creates a dictionary. Inside the function, we start with an empty dictionary named inventory and loop from 0 up to the given size. For each number in this range, we add an entry where the key is the word product, followed by the current index, and the value is that index. After the loop finishes, the function returns the completed inventory dictionary, which lets us easily generate dictionaries of different sizes for testing. We create two dictionaries of different sizes to compare how their size affects iteration time. The first, called the small inventory, is built with a helper function that generates 1,000 entries, where each key is a product label with a number and each value is that number. Using the same function, we then build a large inventory with 10,000 entries. By iterating over both dictionaries, we can observe how increasing the number of elements changes the time it takes to go through all their items. We define a timing function to measure how long it takes to iterate over a particular view of a dictionary. It records a precise start time using a performance counter, then loops through every item in the view while counting how many entries are processed. After the loop finishes, it records the end time and computes the duration by subtracting the start time. Finally, it prints a label for the view, the total number of entries visited, and the elapsed time with high precision. This lets us compare the time cost of iterating over different dictionary views. We begin by printing a message to indicate that we are measuring how long it takes to loop over dictionary keys. Then, we call a timing function with a label for the small dictionary and pass it the view of its keys, so it can measure the time needed to iterate through them. We repeat the same timing process for the large dictionary, using a different label and its keys. Comparing these two measurements shows how increasing the size of a dictionary affects the time required to iterate over its keys. We begin by printing a message to indicate that we are about to measure how long it takes to iterate over dictionary values. Then we call a timing function with a label for the small dictionary and pass it the view of its values, so the function can measure how long it takes to loop through them. We repeat the same timing process for the larger dictionary using a different label. Comparing these two results shows how the size of a dictionary affects the time needed to iterate over its values. We start by printing a message to show that we are about to time how long it takes to loop through the items in a dictionary. Then, we call a timing function on a small dictionary, which counts each item, measures the total time, and prints the result with a label for the small dictionary. We repeat the same timing process for a large dictionary. Comparing these results shows how increasing the size of a dictionary affects the time needed to iterate over its items. This script shows that iterating over dictionary views in Python scales in linear time with the size of the dictionary. It compares iteration over keys, values, and items for one dictionary with 1,000 entries and another with 10,000. The measured times reveal that when the number of entries increases, the time to iterate increases proportionally. This linear behavior is consistent across keys, values, and items, demonstrating that dictionary view iteration remains efficient even as the dictionary grows larger. Efficient set keys. Fast membership checks. Sets are designed to make checking whether an element is present extremely fast by using each element's hash value to jump directly to its location in memory. Because of this, you should prefer sets over slower structures like lists when you frequently need to ask if an item is in a collection. For example, storing block-listed IP addresses in a set allows rapid membership checks even as the collection grows large. In general, sets work best as a yes or no filter over a carefully chosen group of hashable elements, so structure your program to take advantage of this efficiency. For fast membership checks, it is not enough to just use a set. You should also structure your program to build sets once and reuse them. When you need to repeatedly test whether values are allowed, such as validating form fields, convert the list of allowed values to a set at the start and use that set for all checks. In data cleaning, you can similarly keep a set of invalid identifiers and quickly skip any records that match them. By avoiding repeated set construction and relying on these fast membership tests, you take full advantage of hash table efficiency and reduce unnecessary overhead. To keep membership checks in a set fast, focus on how the set changes over time. Adding and removing elements is usually efficient, but very large sets can slow down if their internal storage has to resize often. Instead of repeatedly creating and destroying big sets or constantly rebuilding them in a loop, maintain one stable set and update it incrementally. For example, when tracking active entities in a simulation, keep a single set and adjust it as entities change. This helps preserve an efficient internal structure so membership checks stay quick and reliable under heavy use. Python code. Fast membership checks. In Python, sets provide much faster membership checks than lists, especially when you repeat many lookups. You can demonstrate this by comparing how long it takes to test whether a value is present in a large list versus a large set. Although you pay a one-time cost to convert a list to a set, this cost is quickly recovered when you perform many membership tests. Overall, converting data to a set once and then using it for repeated lookups significantly speeds up membership checking compared with using a list. This script only uses modules that come with Python's standard library, so you do not need to install any extra packages. As long as you have a basic Python setup, you can run the code right away. This makes the script simple to use and accessible for most users. The script starts by importing the time module so it can measure how long operations take to run. This timing is important for comparing the performance of different data structures. By recording how long membership checks take, the code can clearly show that sets handle these checks more efficiently than lists. We begin by creating a large list of integers to represent many user IDs, using a range that goes from 0 up to but not including 500,000. This range is then converted into a list so we can store and work with all these IDs as a single collection. Setting up this large list is important because it lets us later compare how quickly we can check whether a user ID is present in a list versus in a set. Lists are generally slower for membership checks because they must search through their elements one by one. We convert a list of user IDs into a set so we can check membership more efficiently. In Python, testing whether a value is in a set is usually faster than testing whether it is in a list, especially for large collections. This speedup comes from the way sets are implemented using hash tables, which allow constant time lookups on average, while lists require time that grows with their length. By doing the conversion once, we improve the performance of all later membership checks in the script. We create a list of test IDs that includes some IDs found in the main collection and some that are missing. This mixed list is used to measure how fast membership checks run. By combining successful and unsuccessful lookups, the timing results better represent realistic usage where not every search finds a match. We use a helper function to measure how long it takes to check whether items are in a collection. This function accepts the collection and a label that identifies it. To begin timing, it records the current time using the performance counter from the time module. This precise starting point lets us accurately measure the duration of the membership checks that follow. This code repeatedly checks whether certain test IDs are contained in a collection to measure how fast membership tests are. It runs a loop many times, and in each pass it goes through a list of IDs and asks if each one is present in the collection, such as lists and sets, for these membership checks. After all membership checks are finished, the code calls the performance counter from the time module to record the end time. This marks the end of the timing process. With both the start and end times recorded, we can determine how long the membership checks took to run. The code measures how long an operation takes by subtracting the start time from the end time to get the duration in seconds. It then multiplies this value by 1,000 to convert the duration into milliseconds. Using milliseconds gives a finer level of detail, which makes it easier to compare the performance of different operations. The code measures how long membership checks take and prints the result in milliseconds, clearly indicating which type of collection was used. By labeling the timing for each structure, such as a list or a set, it makes it easy to compare how efficiently they can determine whether an item is present. This allows you to see which data structure performs membership tests more quickly. We begin by measuring how long it takes to check whether certain values appear in a list of user IDs. To do this, we call a timing function that tests membership in the list many times and records the total time. We label these results as coming from a list, so we can later compare them with other data structures, such as sets. This gives us a clear sense of how efficient membership checks are when using a list. We now measure how long membership checks take when using a set. A helper function times how quickly it can determine whether certain test IDs are contained in the set of user IDs. And it is given a label to indicate that this run uses a set. This step is important because sets in Python are designed for very fast membership tests. By comparing these timing results with those from lists, we can see how much faster sets are for checking whether an item is present. The code's conclusion is that using sets is more efficient than using lists for checking whether an item is present. Membership tests in a set are generally much faster than in a list, especially when you repeat these checks many times. This speed advantage comes from the way sets are optimized for quick lookups. Therefore, sets are usually a better choice when you frequently need to verify if elements are included. This script compares how quickly Python lists and sets can check whether a user ID is present. It builds a large list of user IDs, converts it to a set, and then repeatedly tests a few IDs that are sometimes present and sometimes missing. By timing thousands of membership checks on both the list and the set, it shows that the set is much faster. The main takeaway is that sets are optimized for lookups, so they are generally a better choice than lists when you need to perform many membership checks. Choosing hashable keys. When designing a set, the choice of key type is important for fast membership checks. Keys should be hashable, meaning they have a stable identity and can be quickly turned into a hash value. Simple, immutable types, such as integers or short strings, work well for this purpose. Using things like student IDs or product codes as keys helps the set stay efficient, so membership tests and updates remain close to constant time. When choosing keys for a set, make sure they are both stable and meaningful for your task. Stable keys do not change their value while they are in the set, so their hash and equality stay consistent. Keys should also match what you consider to be the true identity of an item, such as using a unique email address to represent a customer. By carefully defining what equality means in your domain, you avoid subtle bugs and make set operations more reliable and easier to reason about. When working with large sets or performance-critical code, the efficiency of your key types matters a lot. Keys that are expensive to hash or compare, such as long strings or complex structures, can slow everything down. Instead, use simpler keys that still uniquely identify items, like short identifiers or pre-computed fingerprints. For example, a media library can rely on a short content ID rather than full metadata to keep operations fast. Choosing lightweight, meaningful keys helps your sets remain efficient even under heavy workloads. Python code. Choosing hashable keys. Use simple hashable keys in Python sets to keep membership checks fast and efficient. Comparing simple keys to heavier composite keys shows that more complex structures slow down lookups and add unnecessary overhead. By choosing keys that are stable, meaningful, and lightweight, you preserve the performance benefits of set membership checks while still capturing the information you need. This comment explains that the script only uses modules from Python's standard library, so you do not need to install anything extra. It means the code is self-contained and has no external dependencies. As a result, it is easier to run, share, and set up on different systems. The script starts by importing the time module so it can measure how long operations take. This timing information is important for performance analysis. By tracking the duration of specific processes, the code can compare how efficiently different approaches to managing keys in sets perform. We create a set of simple, immutable keys to represent student ID numbers using plain integers like 101 or 205. Using integers keeps the keys lightweight and efficient, which is important when working with large datasets. Because integers are immutable and hashable, checking whether a given ID is in the set is both fast and memory efficient. We build a set using tuples that combine a student ID with a long descriptive string, creating heavier and more complex keys. These tuple keys are immutable, which is required for use in a set. However, because they contain more detailed information, operations like checking whether an item is in the set can be slower than with simpler keys. This illustrates how adding complexity to keys can negatively affect performance. This function measures how often a given key appears in a set and how long the repeated checking takes. It accepts a set to search, the key to look for, and the number of times to perform the check. At the start, it records the current time and sets a counter to 0. It then loops the specified number of times, and each time it finds the key in the set, it increases the counter. After the loop finishes, it records the end time and returns both the total number of successful finds and the total time spent performing all the checks. We are comparing two ways to represent the same student using keys. One option is a simple key that uses only the student's ID number, such as 205, which is efficient for quick membership checks. The other option is a heavier composite key that combines the student's ID with a descriptive string about their campus location, making it more informative but also more costly to process repeatedly. By contrasting these two approaches, we can see the trade-off between using simple fast keys and more detailed but slower composite keys. We run our membership check a large number of times, 200,000, so we can clearly measure performance differences. First, we repeatedly check whether a simple student ID is in a set of simple keys and record how often it is found and how long this takes. Then, we do the same with a set of heavy keys, using a more complex key but the same number of repetitions. By comparing the results for the simple and heavy keys, we can evaluate which type of key is more efficient for membership checks. The code reports how often each type of key is found in the set and how long those checks take. It first prints the count and timing for the simple key rounded to 4 decimal places. Then it does the same for the heavier composite key. The results show that both keys work for membership checks, but the heavier key requires more processing time, highlighting a performance difference between lightweight and heavier composite keys in set operations. This material explains that when using Python sets, it is best to choose simple, stable, and compact keys for fast membership checks. Basic types like integers are usually shorter, immutable, and more efficient, especially in large sets. More complex composite keys, such as detailed tuples, are valid but tend to be slower and use more memory because they are larger and more complicated. Overall, you should pick keys that match your equality rules while staying as small and stable as possible to keep membership checks predictable and efficient. This script shows that using simple hashable keys, like integers, makes set membership checks in Python much more efficient than using heavier composite keys, built from tuples and long descriptive strings. Both types of keys work correctly for membership tests, but when each is checked 200,000 times, the simple keys run significantly faster. Because they are shorter and immutable, these simple keys also use less memory. The main lesson is to choose compact, stable, and meaningful keys that match your equality rules, so membership checks remain predictable and fast, especially when working with large datasets. Safe, mutable key usage. When using sets, you must be careful with mutable objects as elements because sets rely on each element's hash value staying the same. If an object's attributes change after it is added, its hash can change, and the set may no longer be able to find or remove that element correctly. This can make elements seem to disappear or become stuck, and it can hurt both correctness and performance. Understanding how mutability affects hashing is essential for using sets safely in your applications. When using sets with mutable data, it is best to separate the changing parts from the fixed identity used as the set element. Instead of putting a fully mutable object into a set, store an immutable identifier, such as a unique string or numeric ID. For instance, in a system that tracks user sessions, the session object may change over time, but the session ID stays the same and is what you keep in the set. This lets you perform fast membership checks while safely managing the mutable data elsewhere, and it avoids problems caused by changing hash values. You can sometimes use a custom object that changes over time as an element in a set, as long as the parts of the object used for hashing and equality never change while it is in the set. For instance, A task object might have a fixed task ID that defines its identity, while other fields, like status or progress, can be updated safely. This approach lets the set work correctly, but demands clear documentation and disciplined use to prevent subtle bugs. In practice, it is usually safer to rely on immutable keys for set elements and handle any changing data separately to keep the system reliable and efficient. Python code, safe mutable key usage. This section explains how to safely use mutable objects as keys in sets by relying on stable, immutable identifiers. It shows that if you change fields that affect an object's hash value, membership checks and removal from a set can fail because the stored hash no longer matches. To avoid this, you should keep a separate immutable identifier, such as a fixed session ID, while allowing the associated session object itself to be mutable. The goal is to demonstrate the problem with changing hashed fields and then present the safer pattern that uses immutable identifiers for managing mutable session objects, assuming any required libraries are installed beforehand. We define a class called session to represent a session object whose attributes can change over time. Inside this class, an initialization method runs whenever a new session is created. It takes a session identifier and a status value, then stores them in the new object. The identifier uniquely distinguishes each session, while the status records its current state, allowing every session instance to keep its own independent information. Here we define the hash method for the session class, so that it returns the hash of the session ID. This means the hash value used in hash-based collections, such as sets or dictionaries, depends only on the session ID. As a result, the hash stays stable even if other attributes of the session object change. This stability is important for consistent behavior when the session object is used as a key in collections that rely on hashing. The equality method checks whether another object is a session and then compares their session IDs. If the session IDs match, the two session objects are treated as equal. This means identity is based on the session ID, even if other attributes of the sessions are different. As a result, sessions with the same ID are consistently recognized as the same logical session. We create a session object with a specific session ID and an active status to represent a user session whose attributes can change. This object is then stored in a set that tracks all active sessions. The set relies on the session's unique ID for hashing and equality checks, so the correct session can always be found. Using the session ID in this way ensures reliable lookup, even if other attributes, such as the status, are modified later. The code changes the session object's status to paused, but this does not affect its hash value because the hash is based only on the unchanging session ID. This shows that modifying a mutable field like status does not change how the object is identified in a set. As a result, hash and equality checks still work correctly, since they rely solely on the immutable session ID and ignore the mutable status field. The code checks whether the session object is still in the set of active sessions by relying on its stable session ID. Even if other attributes, such as the session status, have changed, the unchanged identifier allows the set to recognize the same object. The printed message confirms that the session is still found in the set. This shows that using a stable identifier for hashing allows consistent membership checks, even when other mutable attributes are updated. In this example, we use a safer pattern by relying only on immutable identifiers for sessions. We keep a set of active session IDs, which are simple, unchanging strings. Because these identifiers do not change when session details change, we can reliably check whether a session is active. This avoids problems that can occur when membership depends on mutable session objects themselves. We use a dictionary to track session statuses separately from the session objects themselves. Each session has an identifier used as a key, and the value stored for that key is the session's current status, such as paused or active. This lets us update and monitor statuses independently without changing the underlying session objects. As a result, session identifiers remain stable and reliable wherever they are used in the program. We are checking whether a specific session identifier is included in the set of active sessions. This set stores only unchanging session IDs, so membership checks stay accurate even if other session details are modified elsewhere. By relying on these stable identifiers, we keep the changing session data separate from the logic that tracks which sessions are active. This separation helps maintain consistency and prevents problems that can occur when mutable objects are used to control membership. This material explains why objects stored in sets should be identified by immutable values. It describes a session class where each session has an ID and a status, and only the ID is used to determine hashing and equality. Because the ID never changes, updating the session status does not affect whether it remains in the set. The script also presents a safer design that keeps a set of immutable session IDs and uses a separate dictionary to store and update the mutable statuses. This pattern preserves reliable membership checks while still allowing session status to change freely. In this lecture, you learned 2. Explain how hash tables underpin Python dict and set behavior. Analyze the expected time complexity of lookups, insertions, and deletions in dicts and sets. And select appropriate key types and usage patterns to maintain efficient hash-based operations. In the next module, Module 4, we will go over searching techniques. Thank you for your attention. See you all in the next lecture.